Yeah, so today I want to talk a little bit about some of the scalability challenges. I've kind of structured this as a broad brush that just scratches the surface of a number of topics, maybe a little bit more detail than some of the previous discussions, but still just kind of keeping things at a higher level of some of the things we need to attack. So I want to talk a little bit about what we need to do from a scalability and where things are going. Then touch a little bit on the compute side of things and the management side and some things that could be done in the near term to start moving forward and keep the sharks swimming. So I think Mark Seeger set it up pretty well in his keynote. This data is consistent with what he says. It really helps to drive the point home. We are seeing this 2x every year growth in the HPC space in terms of the requirements, and that applies to both the number 1 and the number 500 system. So it's not just like the guys at the top are running away from everyone else. The entire top 500 has got this pattern, and it's been going for many years, going back into the 90s. Now this is significantly outpacing Moore's law, which is giving us a doubling of CPU flops per socket roughly every 2 years, and it's also outpacing the growth of bandwidth in interconnects that are taking about every 3 years to double the wire speeds and move from SDR to DDR and QDR. And so what you see is this significant delta, and it's largely because these other curves, while they're exponential, they're growing at a much slower pace. And so we end up with the situation that we're just going to go nuts on performance requirements. And what that leads you to is rapidly increasing node counts, which is where we're going to have to drive the scalability of open fabrics so we can respond to these node counts. Because we've gotten a kind of a freebie here in that through the use of coprocessor technologies like Xeon Phi, we've seen a big jump in how much power you can get into a single compute node, and that kind of bought us a little bit of time, but the shape of the curves is still on that same trend, and we're going to very quickly be getting into the hundreds of thousands of nodes in order to address even number 10 type systems in the coming few years. So stepping back and looking at the different areas and challenges that this is going to lead to, a lot of emphasis here around power, a lot of emphasis on latency and scalability and memory footprint. And if you step back, Verbs was a great start. It's got us going. But we really need to start looking at how we can come up with better semantic matches. If you go back and you look at the HPC-focused interconnects, you'll see that basically they had a much better semantic match than Verbs has. So that basically takes 100 times more code. That code is consuming power. That code is adding latency, adding complexity, and giving us challenges. So what's happened in the industry is we're kind of back to kind of where we were in 2003. The industry has very well standardized around Verbs. All the vendors are supporting Verbs. A lot of ULPs and applications have been able to build around that Verbs infrastructure, but the scalability requirements are dictating that all the vendors are kind of going in different directions and are getting proprietary libraries for each vendor that are optimized around different concepts and requiring all of the middlewares for the different forms of MPI and PGAS to respond by having many implementations. And I think we need to start recognizing we're kind of back for the compute APIs in the same pattern that we were at in, say, 2003 when we started Open Fabrics to solve the similar picture that was occurring in the Verb side. So what we really need to do as we look forward to these compute is really design APIs and focus around what's needed for the compute side of things. Keeping in mind the low overhead, the need to reduce power, to reduce memory references and memory footprint. All of that is going to cost us scalability. We need to be able to support a variety of different middlewares. There's going to be a continuing variety there, and we need to have an approach that can support multiple hardware vendors so that we can take advantage of this capability. And we need to, as part of this, delegate a lot of the complexity down into the APIs, not only to make the jobs of the middlewares easier, but to allow differentiation and creativity in the hardware vendors as to which parts are moved into hardware, which parts are moved into software, and how they can be addressed in creative and competitive ways, so we can have that healthy ecosystem to spur the innovation. So stepping off of that topic, like I said, I was going to do kind of a broad brush. There's a number of management bottlenecks that we have that are staring us right in the face today within open fabrics. And this is one of the areas that we need to address to increase the node counts. So one of the first and most obvious one is path record queries. We need to recognize that in order to scale up, we're going to need to support a variety of models of how the path record query mechanisms work. In order to support advanced features, we're going to really need to get the applications taking advantage of path record queries. Some of them are hard coding, some of them don't support service levels, some of them don't support P keys, some of them don't support timeouts and things consistently. We need to take advantage of the architecture and the benefits, but solve the problems around that in a scalable manner. And it's very likely that we're going to end up with different solutions at different tiers of cluster sizes. So the small clusters and the medium clusters are doing pretty well with the techniques that exist today. But as we get to larger and to top 1, top 10 type systems, we're going to need techniques that are more topology dependent and can't afford to have huge quantities of data, having 100,000 path records across multiple service levels, across multiple P keys, giving you millions of path records needed in order to answer questions about how a given node could communicate to all the other 100,000 nodes in a cluster, which drives you to, you need mechanisms that allow us to algorithmically construct that, which drives you to needing to have those kinds of mechanisms be a plug-in that you can put into the appropriate places in the cluster, so that you can compute that on the fly based on knowledge with how the routing or the quality of service or the security features of that cluster are being operated, or by that particular topology. And we need to get to the point where we have an API here and get all the ULPs, including those in the kernel and those in the user space, all consolidated using the same API, so that when you throw in a plugin that says, hey, this is the strategy for a 100,000 node cluster with this topology, we come up with the right set of efficiencies and answers to those queries for every app, so that all the apps just work, rather than having some of the apps hard code their perspective of how it should work, and you throw a different topology or a different config at it, and those apps fall apart. And so we need, probably the two most important ones here are the ones that kind of exist right now, is the ability to do the direct mechanisms that exist today and get the caching mechanisms completely worked out, so that all the ULPs and all the benchmarks and all the middlewares are taking advantage of these mechanisms, and then build on from there into techniques that involve replicas and involve opportunities for doing algorithmic approaches. So we had done some work on this a while back, and have done some experimentation. We have a mechanism that's supported in PSM, whereby we can go to an SA path record replica that sits on every node, and then it coordinates with the SMSA. So as the number of ranks per node increase, you can get rid of the need to have 100 different queries coming out of that node, one per processor core. You can instead answer them immediately, very quickly, as jobs start and stop. The information is still there. And this kind of gives you the basis to allow this component here to start becoming algorithmic, or choose different ways of gathering the data. We already have some algorithmic mechanisms in here to deal with partitions and virtual fabrics and service levels and things like that, where some of that can be kind of algorithmically computed, so you don't need to have 100 path records for each potential destination based on all the multiplicities of P keys and service levels that might be viable for talking to that remote node. So jumping to kind of the next broad brush topic that comes up in management is around the essay response time and the scalability and some of the challenges that we have from how it's been architected in Open Fabrics right now. So right now in Open Fabrics, the RMPP implementation is done in the kernel. This works tremendously on the clients, but on a management node, the ASA, where you're getting these queries coming in from many nodes, and the amount of data in a given response may be getting larger as the node count gets larger, the amount of memory footprint in the SA to have all of those queries, especially if some of them are asking the exact same query, is scaling in an exponential manner. So, for example, if all the nodes want to find out who's in the cluster and ask, hey, give me a list of all the node records of all the people in the cluster, in the present implementation of Open Fabrics, there's a separate copy of that identical answer for every client that's made the query sitting in the kernel of the management node, and they're feeding those answers out independently. This is wasting memory. It's basically a significant n-squared type memory waste in the kernel when all the answers are identical for all the people that are asking at the same time frame. So, doing the RMPP in the kernel made a lot of sense for, Open Fabrics clients. Typical client isn't asking that many questions at a time. But for the centralized management model, it doesn't make sense because you've got lots of clients asking questions, you've got lots of concurrent responses going on, and you've got lots of those responses that are similar or identical. So, what you need to do is get to the point of allowing the management side to be able to manage these queries from user space and to use algorithms that may be creative to share the buffering, to keep track of the minimal state per transaction that's in flight, but maybe also do other techniques in terms of pacing and things like that to control the management load in the SA. We've got patches. We've been trying to push them up for a while. It's kind of stalled because it seems to be rather difficult to get things into the OFA kernel work right now, but it's with very minor changes, you can enable RMPP server-side handling, namely on the management nodes, so that you can have this kind of scalability occur. Okay. The next challenge that we have is the SA response time, and we've kind of set ourselves up for a problem here in the way that we've done the APIs. In the API calls, when you go and make a query to the SA, you supply a timeout. Well, guess what? Every app is hard-coding that timeout with some semi-random value that the implementer decided worked pretty good on the 8-node cluster that they first did their implementation on. So they're throwing in a constant like, a second sounds pretty good, half a second sounds pretty good. You get at scale, you need to have these constants be consistent with the capacity and the responsiveness of the implementation of that system. So you can't really have the 50 different apps all hard coding it, and some of your benchmarks stop working because they hard coded in a low value because they were designed on a 2-node cluster, and some of your other apps hard coded in 5 seconds. It sounded pretty good. You need to, let me go back here. We need to get this to the point that there's some centralized configuration here. So that if the administrator or the SM says, hey, I'm dealing with a 100,000 node cluster, some of these answers might take a little bit longer, or the way that it's set up, there's going to be certain characteristics. We need to be able to control that. We also need ways to control the algorithms used for retries and back off. If you're in a very busy cluster, some of the retry algorithms need to be a little less aggressive or have exponential backoffs. Right now they all have very linear backoffs, and oftentimes those numbers are also hard-coded somewhere. The busy response handling is another thing that's in the IBTA standard. We've presented some patches for this as well. Right now the Open Fabrics does the absolute worst thing it could. When the SM says, hey, wait a minute, hold off, I'm busy, what does it do? It immediately retries. Immediately. It should back off and try again, but instead it does the worst thing possible. So it makes the return code of busy from a Fabric Manager totally useless because you're going to elicit the worst response possible. So instead, it's very simple to implement the busy back off so that you pause and delay before you initiate that retry, and then issue the retry later and kind of obey and oblige what the fabric manager is requesting you to do. The next big challenge is around IPRAB and ARP scalability. So, ARP is a fundamental challenge in the IP protocol. We need to have hooks in IPRAB so that once again we can put a plugin in here specific to the topology or the design of the cluster that can do things that work well for ARP. At the mediums and small scales that we're seeing today, obviously standard ARP based around broadcast is kind of working. As you get larger, we need to have ways to preload these tables or algorithmically compute it with a knowledge of how the IP addresses have been assigned for the cluster. All the big clusters I've been involved with have a very algorithmic approach to assigning IP addresses. They're not just randomly picking them out of some bucket. Often it's like node 1 has IP number x.1, node 2 has IP number x.2, etc. Right? So by knowing that algorithm, being able to have a plug-in methodology, when you get to the highly scalable systems, you can start to take advantage of those algorithmic approaches. When you're on the medium or the small systems where it may be a little more ad hoc or it may be changing more dynamically because it's an experimental system or a university system that runs a lot of different environments or experiments on it, then you can use the more traditional approaches, but oftentimes those systems aren't 100,000 nodes. The guys that are building a 100,000 node cluster aren't going to be walking around recabling it daily or changing how they've decided to set things up, but they're going to want to set it up, have control and choices that are appropriate to their environment, and have the ability to set up a very efficient way to solve these kinds of challenges. So we need to really have this all tied in, and this kind of an API needs to also really tie into the path record methodology because there's going to be some continuities here. Obviously, if we can algorithmically figure out from an IP address lid information, we should be able to algorithmically be able to figure out other information about the path record for those kinds of clusters. So having this all tied in a scalable way will give us the ability to really scale. So, in summary, we're going to really see the cluster growth. I mean, the growth is sitting right in front of our face. You don't have to do any serious data crunching. Just look at the trends in the top 500. It's very easy to get that data out of the website. It's very easy to look at the trends that we've seen in processor performance and how many flops you get per socket. So the math is trivial to conclude that, hey, we're going to be hitting huge scale in these kinds of clusters very quickly. Most of the top 1 systems today are around the 100,000 node or thereabouts already. OpenFabrics has been growing, and its presence in those clusters, if we want to participate, we have to respond, or otherwise we're not going to be able to even participate in those kind of clusters. The compute stacks are starting to migrate back towards a very vendor-specific approach. We need to figure out how we in OpenFabrics wants to address this. There was kind of a call to action earlier today about we need to lead in this space rather than follow. We need to establish the software looking from the application perspective down. What do we need for these middlewares? And some of them it's more obvious. Some of them there's obviously a lot of alternatives still being tossed around. But we need to figure that out from the top-down perspective, as one of the previous presenters pointed out. The present implementation of IBTA management has gotten us pretty far so far, but we've got some very obvious problems, and a lot of the apps have been avoiding those problems by kind of working around it or hard coding stuff, and it's just a recipe for difficulties. I mean, people are having problems that some of the more advanced features that exist in the standard don't work with all the apps because they're trying to work around this. We need to really have a solution that scales here and do it in a manner that allows creativity to deal with the kinds of things that will be necessary to be efficient at 100,000 nodes, both from a memory footprint perspective and an efficiency of coming to the answers and effective ways to distribute the workload of coming up with those answers. There are some near-term things that we've been able to identify. There's still things that are sitting in the queue to be pulled in. But I think we need to get the shark swimming again on some of these minor things so that we can start to really get rolling on the important things, or else the world will pass us by, right? And we really need the flexibility on the long term. We really need to have things that are designed around a plug-in type concept, because we're going to need different types of solution at different degrees of scale, and some of the things that are going to need to be done at the 100,000 node scale are going to be radically different than what's being done today in order to get the scalability there without costing power and memory and other factors. So we really need to take that call to action and get ourselves swimming rapidly in these directions and have the right degrees of flexibility in there so that we can be creative about the answers. So in some cases, maybe the end user of a huge cluster has a preferred way of doing things and tweaks the implementations of the plugins and whatnot. Okay, well, thank you.
Any quick questions? Yes.
Same question that was asked earlier of as far as getting this stuff into OPED, contributing the source, and taking some of these thoughts and ideas that you've got back to standards bodies and standardizing some of these approaches. Where is Intel on its feeling about that? Is this sort of what you want to do in an open source environment or a standards-based environment? Or is this Intel proprietary? Where are you going with it?
As I indicated, the first batch of all these things we've been trying to get in for a couple of years now. They've been sitting in the queue. We need to get the shark swimming. New innovation in the kernel side is been sluggish for Open Fabrics, and we need to really get that moving and start getting these in so we can build the building blocks that are needed to build some of these other concepts in there. We've open sourced PSM, and that's been part of Open Fabrics for 3 years. That has some of these concepts in it as well.
Well, I'm thinking about the management part, particularly your middle bullet there, OFA implementation of IP management will be bottleneck. Is that to say that the management as specified and spec today is sufficient, just the implementation, or we need to go back and take a look at the basic architecture itself?
Well, the basic architecture is essentially solid. I mean, you're seeing, we need a centralized management approach to these problems. There's a lot of implementation details that really haven't been paid attention to.
Any other questions? Thanks very much.
All right, thank you.